All right, so good afternoon. This work is called It's Not Just About Accuracy, Metrics That Matter When Modeling Expert Sketching Ability. This is a pretty collaborative project between Texas A&M and Georgia Tech and funded by the National Science Foundation. My name is Blake Williford and I'll be presenting it. Essentially what we were after was teaching engineers sketching skills. So one of the initial things that we wanted to do was see how novices and experts sketch differently. I always like to start with talking about the benefits of drawing. It's one of these undervalued things, I think, in society. It can benefit your internal thought processes. It can improve your problem-solving ability. It can improve your visual communication ability. It can encourage collaboration. We've all been in whiteboarding sessions and so forth. It can improve your spatial reasoning. It can elevate your attention to detail and your awareness of details in the world. It's very closely tied to creativity. It's uniquely tailored to individuals. And so much more, and I would even go so far as to say that it's something maybe all people should learn. We focus in this work on a particular form of drawing called sketching, design sketching, that is more oriented towards communication. So everybody's kind of drawn a map for someone or just doodled something to explain a concept to someone. It's kind of more oriented that way. And we teach it in this very sort of design sketching, industrial design way in which all of these fundamental primitives are the fundamentals that you should practice, from which you can then combine them to form any three-dimensional object from your imagination. So if you break it down this way, it's a great way to learn sketching comprehensively. So you can imagine, see here you have a cylinder and you have void shapes. That's a camera there, right? So by learning it this way, you're teaching yourself how to use the ABCs of sketching and draw anything that you can imagine. The problem is it's difficult for many people to learn. People have low confidence and self-efficacy with respect to sketching. They struggle with motivation. You have all kinds of access issues because schools don't adequately fund this type of stuff. They don't seem to value it as much. And furthermore, there's really even a mentality issue. I think that a lot of young kids stop sketching at a certain age. They stop pursuing creative activities, which I think is a shame, but research has shown that. So the motivation of this work is really seeing what are the differences between novices and experts in terms of how they sketch. And the long-term goal was how can that understanding lead to automated, intelligent feedback when learning sketching, right? There's been a lot of cool prior work in this space, but just for sake of time, we'll just talk about how we're kind of different. We're influenced from this design sketching pedagogy, which is really from industrial design. Again, we're kind of doing this comprehensive approach where you're not learning how to draw specific things like a portrait or a car, but rather this general, all-encompassing approach to learning sketching. And then lastly, we're really exploring a lot of this sort of game-based learning and gamification as well. Not so much in this work, but in some of our other work. So what we've done is we've built this platform called SketchTivity, which is an intelligent tutoring system for practicing these sketching fundamentals. And what it is it's a web-based tool where you can go on and you can practice all of these basic shapes, including cuboids here and different perspective orientations, which is exactly what you would do if you took a design sketching class. Here's some pictures of students using it. Just to briefly touch on the recognition system, we typically do some resampling because when you sketch on a tablet device, the information comes in as X, Y, and time-stamped coordinates, and it can be quite noisy. So we'll typically do some kind of resampling where we make the points equidistant. We'll also clip tails and hooks off. That tends to happen especially with hardware because of just the nature of hardware, like little hooks and clips happen. And then we typically will do some kind of segmentation as well. So if you were to draw a square as one single stroke, you would have basically, it would be harder to do some of the operations I'm going to talk about in the feature collection that we do. So what we do is we use a corner detection algorithm that we've developed in our lab called short straw, and that allows us to break that into different strokes that we can analyze individual strokes. And then lastly, to recognize these different shapes, these different primitives, we have sort of these unique recognizers. We don't really do template matching because the shapes are in all different types of orientations, so the template matching wouldn't quite work well in that context. So we actually literally look for like 12 sides and 8 corners in a shape like a cube, right? Our system is very robust. Now, granted, each of these lessons, it's looking for that specific form. So you would expect to see accuracies around 100%. The only reason that it's not is because sometimes there's user error. So sometimes people don't draw a cube correctly or something. So for example, you can see there the cuboids drops below 90%. So what we did in this work was we looked at 24 different features that we thought could differentiate novices and experts. And a lot of this was driven by talking to the domain experts and seeing kind of what are the different things that are important in drawing. Obviously, accuracy is one of the most obvious things in drawing that you want to look at. We look at things like Euclidean distance. So if you take a line and you look at the Euclidean distance away from the perfect line, that's one way of looking at accuracy. Hausdorff similarity is basically a template matcher that you can use. Pretty standard stuff. Speed is something that is unique to hardware, right? As a human, you can't really detect the speed of a sketch. It's just something that's there. You don't know. But with hardware, you can actually look at how fast people draw. You can see a lot more in the paper, the different formulas we use. Smoothness is a really interesting feature. So you're really encouraged in sketching and design sketching to draw smoothly and fluidly. And we can actually detect that with sketch recognition. So what we do is we look at the angular rotation of these different points in a line. And we can either average them or sum them. And basically what this measure is kind of like a measure of jitteriness. So if this value is very high, you're drawing like a jittery, shaky line. And if it's a low value, then it's very smooth. We do have a novel approach for curved shapes. So for example, circles and ellipses, we actually essentially kind of unfold that shape into a line, and that allows us to get a smoothness feature just as if it were a line. Speed fluidity features are pretty interesting. These are looking at how speed changes throughout a stroke. So you're encouraged in design sketching to draw with like a sort of even speed as you draw something. And these features kind of allow us to sort of see if someone's doing that. And then lastly, there's planning features. So number of strokes, the order in which you draw things. These are all very interesting things because in the pedagogy, the way you're actually taught to draw primitives and draw shapes as the individual strokes. You're encouraged to break down the shape as opposed to sort of drawing a square in one stroke. You're encouraged to draw it in 4 separate strokes. And these features allow us to kind of get a sense of what they're doing. And then lastly, we do a few combined features that are just basically different ratios between smoothness and speed and accuracy and so on. What we did was we collected data from novices and experts. We had 20 different engineering students from Georgia Tech who were enrolled in a mechanical engineering class, and they would practice all these different basic forms. We had experts practice all those different forms. The experts were typically teachers. They have experience teaching sketching and doing it professionally in an industrial design context or a concept design context. And then we did a statistical analysis. This big scary looking graph, really what it's just showing is that these are the features that had really high statistical significance. And so not just below 0.05, but well below, like below 0.01. So these are very significant features. And so these became the subset of features that were actually useful in our classifier for differentiating novices and experts. And you can see here that we did a random forest, 10-fold cross-validation. Here's showing kind of the accuracy we have. And I put stars next to ellipses and cuboids, right, because these values are actually quite high. So if you draw a cube, if someone off the street draws a cube and you have an expert draw a cube, we have 98% accuracy in determining that that's an expert. And a lot of that is because cubes are more complex forms, especially if you're drawing something in perspective, whereas something like a line, there's a good chance someone off the street could draw a decent line, right? So you do have more accuracy when the forms are more complex. From this, we were also able to create sort of this holistic score. So we had 2 experts rank drawings of these basic forms, and then we used a similarity score to ensure that they were in agreement, essentially, these 2 experts. And That was a p-value less than 0.05, so that's significant. And that allowed us to create this holistic score where we basically can kind of say, does this sketch of this basic form sort of approach how an expert would sketch it? And we have, p less than 0.05 for all the different shapes, including lines, circles, squares, cubes. This quality score is basically an internal metric. So this is not something that we show the user per se. This is more to show, it's more to drive kind of how the system can facilitate maybe saying, you should practice this form some more, you should improve your smoothness of your line work in this form and that type of thing. It's more of like a general, all-encompassing score. What I think is really most interesting about what we discovered is what the real differences were in terms of the features between novices and experts. One of the things was accuracy. So you would expect experts to be always more accurate, but not necessarily. Circles and ellipses, they actually were not necessarily more accurate than novices. They did sketch things much faster, and they did sketch things with much smoother line quality, much smoother line work. So they were essentially sacrificing accuracy sometimes for fluidity, like the speed and smoothness of the line work. Planning-wise, they sketched primitives with more strokes, so they would break a cube down into its 12 sides, whereas a novice might try to draw the whole cube in 1 to 2 to 3 strokes. Experts are taught to kind of break it down into the individual lines. Ratio-wise, we found the ratio of average deviation, average speed as being significantly different within like a specific form, right? So when students draw at a speed equal to an expert, their accuracy will be worse, and vice versa. And again, overall, there's this tendency for experts to sort of sacrifice accuracy for speed. So in other words, it's not the most important thing when they sketch, which makes sense because sketching is more about ideation and concepting, not necessarily you making photorealistic images. That's driven a lot of our future work, so now we're trying to think about the interface and how we can, on the user interface side, the user experience side, show users where they can improve in terms of these things like accuracy, smoothness, speed, and give some sort of humanized feedback as well to sort of help them practice these sketching fundamentals. We also want to look at things like pressure. At the time of this data collection, pressure was not really ubiquitous. Nowadays, just a few years later, it's like everything is basically taking in pressure now. So iPads, Surface Pros, everything takes in pressure. We also want to take advantage of metrics that can be obtained with only sketch recognition. So speed is one of those, right? You can't really recognize speed by just looking at a flat image. And then lastly, we really want to work towards ultimately kind of like a virtual instructor, which has been talked about a lot in this conference, right? Some kind of intelligent agent. Similar techniques can be used to determine students' confidence in their diagrams for our other project in our lab, which is called Mechanics. It's a system that allows people to practice free body diagrams. Feel free to contact us if you're interested in using this or the SketchTivity platform, because they are designed for integrating into classrooms. And then lastly, I just want to tie this to sort of a bigger picture idea in other domains. Is anybody a musician here? A few of you? In music, there's a blues scale, which is basically a minor pentatonic scale, but it has an interesting little caveat, which is that it has a flat fifth added. And a flat fifth is the most dissonant interval in music. It sounds awful. So if you play the root note and that note together, it's the most dissonant possible notes in Western music. And yet, it gets used all the time in music. It gets used a lot in blues, jazz, and so on. So what that really means is that it's not so much about the accuracy as it is about the overall composition. And I think the same is true in sketching, right? Sometimes a sketch doesn't have to be perfectly accurate, but if it's smooth and it's fluid and it communicates an idea, that's the most important thing. So our mission is that anyone can learn to draw. That's what we're kind of after with this work. So thank you for listening.
couple questions before
Yes,
we
sir.
finish up.
Find you.
Hi, Andreas Butz, University of Munich. With these analysis that you do of the artistic stroke, can you use them in the other direction? Like, for example, taking a sketch of a layman and then analyzing and redoing it with the stroke of the expert and showing the layman how it could have been done better?
Right. We sometimes call that beautification. So you could take a stroke done by a novice and you could just automatically improve it to like a perfect stroke, as well as also kind of show them, here's what you should improve in that stroke. So yeah, absolutely, you can do that.
Other questions?
Hi, Kashyap from Aalto University.
Hi.
I had a question. Can machines learn how to sketch using what you presented? Because one of the important aspects of sketching, I feel, is that it's not something that's perfect, because that makes it look more like a finished product.
True.
In contrast to a sketch, which is like an ideation process. So can machines sketch using what you presented?
Well, when you ask that, do you mean can machines sketch in this imperfect, messy way?
Yeah.
I mean, I think it's theoretically possible. It's not something that we're super focused on or interested in because we're really focused on the human side. I consider myself a humanist. I'm really more interested in humans learning sketching more than anything. Although I think it could be interesting if machines could learn to sketch, that might make them more powerful teachers. That might make them a more powerful agent or something that could help you learn to sketch, which I think would be interesting.
Thanks.
As well as for co-creative systems, right? If you sketch something and the computer is also be able to respond with a sketch, that's pretty powerful.
Hi, thanks for the wonderful presentation. Subhashri here from Syracuse University. My question to you is that I'm just wondering if you notice certain differences between novices. So were some more adept and quick to catch on to what experts were doing? And even like experts can have different styles, right, which might match novices better. So I'm just wondering if you have considered how to maybe match certain styles of novices and experts and just to make the platform more adaptable.
Totally, yeah. I mean, everybody's different. Even expert, like you watch people that have been drawing for 20 years and they can't draw ellipses that well. You know, ellipses are tough, right? They're circles in perspective and they're kind of tricky. So yeah, and then like you said, there's also a lot of different styles and approaches to sketching. So, you know, this work is by no means like a comprehensive look at all people, all possible people. I think the important thing moving forward is, like you said, is to sort of keep it adaptive and flexible and don't really, you know, get in the way of people's own styles. These things like accuracy and having good line quality and smoothness, those are generally good principles. Like you should have those things if you want to sketch well and if you want to communicate an idea well. But other than that, you should be encouraged to kind of have your own style. So.
And we have time for one final question, if there's any.
Thanks for all the questions, yeah.
Okay, I actually wanted to ask then, do you feel like these metrics that you're tracking, that users will be able to understand them and use them to improve their own sketching? Or do you expect the system to interpret those in ways that it gives more specific feedback?
I think the metrics that we discussed here, I think they're really more internal to the computer. I think that the metrics that are kind of more useful for people is kind of what we showed in this screenshot here, where you can just show some accuracy and the smoothness and the speed. But I think that these metrics are really more for the machine getting a sense of building a user model, right, of how the person is performing. So.
If it's quick.
I just wanted to expand upon this question about drawing, the computer drawing, right? So the computers already do draw a lot in architecture, where I think this work could, you know, like when you have a plan, they say if you give them the cleaned up version, they won't change it, but if you give them a messy version, they'll change it. So architecture already does produce sketches, but what I think would be really nice for this is this idea of making it appropriately messy compared to how confident someone is with the idea. So the messiness of the sketch is representative of how far in the design process you are and how clean your idea is, how far you're to the finished product, and that's where these features, I think, could play a really good part.
That's Dr. Tracey Hammond, by the way, so she's here. So she's here with her 3-year-old and 6-month-old, so come say hi. That's one.
And let's thank our final speaker.